I'm Andre Andriola,
I'm Patrick Gervin.
I'm Charlie Alexander.
and this is Design Phase 3, Team 12. So, to start off, we will begin talking about project management, and then we'll get into the project architecture as a whole, and then we'll get into the industrial design, and then we'll look at the individual CAD models for each individual piece that make up the whole project. And then we'll look at the prototype, which is basically just putting all the CAD models in an actual design. And then we look at the economic analysis for the project's future, and then that's when we'll look at the whole group's project future. So for project management, first we created a Gantt chart, which had a total of 12 tasks. Now at the beginning, we actually had 11 tasks, and then we decided to add CAD models. And from DP2 to DP3, we changed concept testing and CAD models into Phase 3, where they were originally Phase 2. And then if you look over at the DSM, it breaks down the individual tasks on when they can be done and when the next one can be started. So if you look, customer needs has to be done before target specifications can be done. And then if you look back at the Gantt chart, we have the prototype just got finished today, and then the presentation is due tomorrow, which wraps up our project. And then if we look further into it, I already talked about the revisions of the Gantt chart, and then the CAD models and concept testing have been completed. So that means tasks 1 through 11 have been completed up to this point, leaving only the presentation, which will be completed tomorrow, leaving us on time. And that means we had to be efficient from adding DP2 to DP3, the concept testing and CAD models. So as a group, we worked it out and we did an excellent job with that.
So now we're going to talk about product architecture. The product architecture that we have designed is shown here in this schematic. It allows it easy to be worked on during its development. So during the development, individual people can work on, and individual teams can work on each individual block shown here. It also allows us to launch derivatives off our platform product, which is the BRG itself. So you can change any one of these blocks here slightly just to change the product in a small way without extremely changing the design and changing the purpose of it. So if you look at the sketch here, the blocks represent individual chunks, and in red describes the function of the part, while in blue describes the actual physical component. So for example, the entrance ramp sets the ball speed, and here to turn the wheel, which is over here, this entire chunk is made up of 3 individual chunks. The Arduino sketch, which gives user input, the Arduino itself, which is the power and breadboard, and the servo motor and axle, which transmits power to the wheel to raise and move the ball through the course. So if we change, for example, the wheel to any other moving part, such as a treadmill, we can change the BRG only slightly, but launch it as a different product. This allows us to easily change the design, launch new products. You can swap these blocks with each other and make it work, add new blocks, change blocks, whatever needs to be done. But this allows us to make derivatives of this product. So when we release the BRG, once we start getting it out of phase, we can start launching similar products, maybe more complex products, target new subjects other than physics, target different age groups. We can basically change it however we want. So it makes the BRG an effective platform product for the future. Second, we're going to talk about the industrial design. So in here, this is a list of the ergonomics and the importance that we have ranked them. So for example, ease of maintenance was ranked as extremely high. We gave it a maximum value. And this is because it needs to be easily maintained. If the BRG breaks within the classroom, the teacher and the students cannot use it. They're going to have to fix it. They're going to have to spend time. They're going to have to waste their class time. It's the opposite of what this is supposed to accomplish. The BRG is supposed to be an effective use of class time. They implement it, the students learn from it, and by breaking, it's completely eliminating that. Also, if it's a critical break, that means they either have to purchase a new BRG, and they probably won't be too happy with us, so they may not want to buy a new one, or if the company decides to supply them with new parts, they have to be shipped out, to be manufactured. It's going to take more time. So that has been ranked as a high one. This entire ergonomics is based off customer interaction. So as you can see, ease of use is high. We want the students and teachers to be able to use it very easily. It should not be too difficult. We want the user to have interaction with it. We're not worried about the quantity of user interaction as much as we are of the quality. We want the brief interaction that the students have with it to be effective. It doesn't matter if it's a brief interaction or a large interaction. All that matters is that it does the job of effectively teaching the student about physics. And finally, safety was ranked as a high since it's been being used in a classroom. Although safety isn't much of an issue for this product because there's nothing that can really go wrong with it. The biggest thing that could happen is possibly being shocked by the breadboard of the Arduino, but it's highly unlikely to happen. So secondly, we have the aesthetics, and they're also ranked in the same fashion as the ergonomics. So product differentiation was ranked medium to high. The BRG needs to be a little different to set itself apart from other products on the market. We want teachers to see it and be shocked by it. They want to go out and buy it. There's a lot of educational products on the market, so by setting ourselves different, they may be more apt to purchase it. Also, students will be more apt to use it and have fun using it if it's unlike anything they've used before in a classroom setting. Pride of ownership, we ranked as medium. The purpose of the BRG is to educate, so the image of it is not extremely important. And finally, the team motivation. We rank team motivation relatively high. If the team is highly motivated to create the BRG, we can effectively create new ideas using the product architecture we described earlier. And if it promotes team motivation in the classroom and the students and teachers are having fun using it and want to work as a team to use it, then they'll get the most use out of it and actually get an educational benefit from it.
So instead of being in DP2, we have our CAD models in DP3, and so on this slide we have the mock-ups of the wheel, and so we have one axle going through it, and then the other two are the support, which will hold the ping pong ball, so when the wheel rotates, it'll take the ping pong ball from one ramp to the other. And then on this slide we have the two ramps that are different size. So the first one is a 2x2x2, which will take the ball originally from the first downhill ramp with the speed and then carry it to the platform. And then the other one is higher, so that way it can, once the ball is delivered, it will drop off and it will gain speed, enough speed to go up the ramp at the required speed. And this one is a 2x6x2. And here's a picture of our prototype after many hours of contemplating how tall the ramps need to be, how we were going to connect the servo motor to the wheel, and how we were going to get the wheel to turn from the one ramp to the other. And so for our economic analysis, this is our manufacturing time cost table. So our basic three components are the entry ramp, the exit ramp, and the wheel. So the entry ramp and the exit ramp are both made of styrofoam, which is a pretty cheap material. And so it doesn't take much to assemble, so therefore it's a lot cheaper than the wheel. And the wheel, we used a plastic mock-up of a circle that we found. And so it's because it's a lot heavier, it's also much more expensive compared to the styrofoam. So we also decided that it was going to take twice as long to make because the circle needs to be like more precise to say, because if it's not precise, then it won't spin correctly and then the ball could go any which direction. So as a result, we made the assembly time much longer for that. And as a result, the price for the labor and for the material is a lot higher for the wheel. And so at the end, our total cost for these parts is $1.08. At the bottom, we have the material costs, the processing time, and then no information on the mold because we don't actually need to make molds. For the project future, we have a project detailed design, including how the parts are manufactured, what is the process, how does the process fit the design, and then is the product ready to be mass produced. After that, we need to do more complete economic analysis in order to determine whether the company is ready to launch. The third thing is to allow the prototypes to be tested in the high school environment to see if they are sturdy enough and will they sustain for multiple trials. They also need to collect feedback from peers and our instructors on how we can improve the project for future engineering endeavors. And so for any further questions, please contact Team 12. Thank you.
Thank you.